All right, I'll go ahead and begin the meeting. So thank you all for attending this month's meeting, all virtual. I know typically we have a in-person and Zoom meeting at the Lindsay Wildlife Museum, but they have our room with a bunch of trick-or-treaters tonight, so we're doing it all on Zoom. Pretty simple agenda this evening, so thank you and welcome to the October all Zoom general meeting of the Mount Diablo Astronomical Society. This evening we have Professor Thomas Madura speaking to us. I cannot move my slide forward. There we go. Okay. Quick reminder that we are still looking for a program director. So all this great content that we're enjoying with our general meetings, Dick Flask has been doing it for decades for us, and it's time to pass the torch. A very important position, and also I think exciting getting to interact with scientists and professors and teachers and just general laymen who are experts in the field of astronomy and getting them to speak with our club. So if you are interested, please let any of the board members know. You can email me directly. It's an important position for our club and something that we could use some help on. We're also looking for a new treasurer. Beth Rainsford has been doing it for years as well, and it's time for her to move on. So anybody looking to help with just keeping the books for the club and also just getting to get more involved on the board, it's a lot of fun. We've finished up our public astronomy nights up on Mount Diablo, last month, so we'll be restarting those again next year in April. As you can see on the calendar, we have several school events, though, public outreach events. So if you can help out at all, MDAS.net, all the information to RSVP and help out with those events is there. All right, so I'm going to quickly introduce our speaker of the evening. Dr. Madura is an associate professor in the Department of Physics and Astronomy at San Jose State University. He is a theoretical and computational astrophysicist who specializes in the study of massive stars, as well as astronomy outreach and education for students with visual impairments, which is pretty interesting. He received his PhD in physics from the University of Delaware. During his 4 years working as a scientist at NASA's Goddard Space Flight Center, he developed a program to 3D print astrophysical objects to help teach astronomy to students with visual impairments, and he has expertise in various 3D printing technologies, having produced the first 3D print of a nebula based on astronomical observations and the first 3D prints of a supercomputer simulation of an astrophysical system. He is currently the principal investigator of a $1.5 million National Science Foundation research grant aimed at developing and studying the use of 3D printed technology for astronomy education in students with blind and visual impairments. And he's going to be giving us another presentation of that next February, so be looking forward to that. So I am going to stop sharing and welcome Dr. Madura to Madura. I apologize. We'll go ahead and let you start sharing your screen.
Great. Can everyone hear me okay? I assume everyone can hear me okay. So so thank you so much for this opportunity to come back and to present about recent advancements in our understanding of the colliding winds in the Wolf-Rayet binary system WR140. So this is the JWST image, or one of the JWST images that I will be talking about. So for those of you who may remember, I like to use the last time I gave an MDAS talk was back in 2023 with some of the very first observations that came from James Webb. And they were part of an early release science program. And back then, the talk that I gave was on these JWST observations of this colliding wind binary known as WR140. So when I last gave that talk, I kind of presented a little bit of background on this binary system. So it is a evolved Wolf-Rayet star, a massive Wolf-Rayet star, about 10 solar masses currently. It's classified as what's known as a WC7 star. The C just means carbon, so has a carbon enhancement, which will be important. We'll talk about the role of carbon in a little bit. And then there's an O star companion in a very elliptical orbit with a mass of about 29 solar masses. The distance of the system is about 1.6 kiloparsecs, and the period is just under 8 years. And the nice thing about WR140, it's what we call the canonical colliding wind binary, or the Rosetta Stone colliding wind binary. What I mean by that is we have very good observations of this system, and we know the orientation of the binary orbit really well. So I have in the lower right corner, there's an illustration of the binary orientation on the sky. We know the orbital parameters very well. So it serves as a great astrophysical laboratory for studying massive binary star systems and this phenomenon that we'll be talking about, which is colliding stellar winds. So back in 2022, these were the observations that were taken by JWST. There was a NASA press release about this. And what we are seeing in the image on the left are rings. And these rings extend several tens of thousands of AU from the central binary system. And what we are actually seeing are shells of dust and molecules that are being formed in the compressed stellar winds. And this result was a little bit surprising at the time because we were shocked at the number of rings of dust that we were able to actually image. So we expected to see some, we knew we would see some, but we didn't expect to see them so prominently and extend so far out from the system. And it just goes to speak to just how fantastic James Webb actually is. We actually were pushing the detection limits of James Webb with these observations. So there are probably actually even more rings of dust that extend even further out into the interstellar medium. But James Webb just isn't sensitive enough to detect those farther rings. And then the images on the right are kind of cleaned up, zoomed in images near the unresolved central binary, unresolved by JWST, and where the very first shell of dust formation was created, or at least one of the most recent shells of dust that was created. And what's going to be important is going to be this feature called C1, which is just a dust feature that we will be talking about in a little bit more detail, because it's actually, to give away a little bit of what we'll be talking about, we are able to actually see these dust rings moving and get proper motions for them. So one of the things that you'll notice, I'll go back here for a second, is at the center, especially on the image on the left, there are diffraction artifacts that are due to the structure of the James Webb Telescope. So I'm sure most of you are probably familiar with the structure of the James Webb Space Telescope by now, but there's a primary mirror, and then there's a secondary mirror that is supported by struts. And as the light comes in, it will diffract around those struts that support the secondary mirror. And so you will get diffraction artifacts. And so one of the things that we said was that we knew about the diffraction artifacts. So these are highlighted in the yellow contours in this image. And then there were these other features that we believed were astrophysical in origin because they didn't line up with any known instrumental artifact, right? So we were very confident that these were real. And so to prove this, one of the things that we did is we wanted to do follow-up observations with James Webb so that we could see if we could get proper motions and to also confirm that these are real features and not just instrumental artifacts. We also had a dust model, so we were also very confident that these were real astrophysical origin dust rings because we came up with a geometric dust model. And I'm just going to show, I'm not going to speak much about the dust model today, other than to say that we had this dust model that was able to reproduce relatively well what James Webb sees. So this is actually an extremely simple, just a simple geometric model for the dust. And we found that this geometric model actually matches up really well with the features that we believe to be real. So on the left is obviously the JWST image at 15 microns. And then on the right, we have the geometric dust model, which does not have the diffraction artifacts. The other thing that we did with the very first set of observations back in 2022 was to get spectra with the JWST MIRI instrument. And what we found were basically carbonaceous molecules. So we found carbonaceous grains of dust. We found polycyclic aromatic hydrocarbons that are formed by carbon-carbon chains. And we also found some other H-free or hydrogen-free carbonaceous grains. And this will actually be important for understanding some of the chemistry that's going on, some of the astrophysical chemistry, because most of what we are seeing is actually hydrogen-free or hydrogen deficient. And that actually will turn out to make sense because the star, one of the stars in the system, remember, is this WC Wolf-Rayet star, which has a lot of nuclear process material, and so it's carbon enhanced. So we'll end up coming back to that point. And so one of the other big points about all of this is trying to understand some really important questions. So the questions that we're trying to answer here are, do we understand the composition and the formation of dust and complex molecules? And do we also understand how this dust and these complex molecules survive and make it out into the interstellar medium? Now, why do we care about dust? Well, if you want to form more complicated things like planets and planets that have atmospheres and then eventually life, we need to understand astrophysical chemistry, and we need to understand where all of the building blocks for things like planets and life come from. And massive stars, we're discovering that these evolved massive stars are actually really good places and really good ways to seed the interstellar medium with the complicated molecules that are necessary for forming other important objects like planets. But the problem is that we don't really completely understand astrophysical chemistry because it's astrophysical. It's very different in a lot of ways from the chemistry that we're used to here on Earth, and that happens naturally in the Earth biome. And so we're trying to understand, okay, do we actually understand what this stuff is? How does it form? But one of the other big mysteries is, how does this stuff actually survive? Because these massive stars are really massive stars, and they're very hot objects. Wolf-Rayet stars tend to be on the order, they can be 40, 50,000 Kelvin. Same with O stars. They can be temperatures in the tens of thousands of Kelvin. And they're emitting very harsh radiation fields. There's a lot of ultraviolet radiation that's coming out. And so it's a little surprising that things as delicate as dust and polycyclic aromatic hydrocarbons and stuff are surviving when they're being bathed in these very intense radiation fields. So how is this stuff forming, and how is it surviving, and how far can it get when it survives? So these are the types of questions that we are trying to answer with the various JWST programs. So one of the things I'd like to do is just review really quickly how these Wolf-Rayet O-star binaries kind of work. And what I mean when I'm talking about colliding stellar winds and shocks and dust, I'm going to give a little bit of a better idea of what these terms mean and where things are forming. So we typically have a Wolf-Rayet star and a massive O star that form a binary. One of the things that's very interesting about massive stars is that almost all massive stars are in binaries or higher order systems. Population statistics show that basically like 90% or more of massive stars are in higher order systems. And it turns out that these massive stars are extremely hot and extremely bright. And they're actually so bright that the radiation coming from the stars will couple to the atoms that are in the outer atmosphere of the stars, and there will actually be an enormous radiation pressure that propels a mass outflow out into space at millions of miles an hour or thousands of kilometers per second. And this is solely due to the fact that, of the composition of the atmosphere of the star, and also just its intense radiation field. So these stars have significant mass loss rates due to this radiation pressure. And it turns out that when you get two massive stars in a binary where each has a stellar wind being blown off into space, these two stellar winds can collide with each other. And when they do that, they form a shock front where the winds meet. And in this shock front, all kinds of interesting physics can happen. And it is in this shock front where we believe that, or where we believe and kind of know that the dust is forming. And that's where kind of all of this chemistry is happening. And then as the two stars kind of go around in their orbits, especially if they have like either a nice circular orbit or a very eccentric orbit, the dust will form a spiral pattern as the two stars are going around, and then the dust will flow outward close to the terminal speed of the winds of the stars. So the terminal speed is basically just the maximum speed that the outflow from the stars can reach. And then it just kind of just keeps flowing out into space. Now, to help illustrate this, one of the things that I do is I do numerical simulations of this effect. So this is a supercomputer simulation of a colliding wind binary, one that's very similar to WR140. And so what you're seeing on the left is a slice in the orbital plane from the 3D computer simulation. And the color is showing the density on a logarithmic scale of the material that's coming off in the stellar winds. So the stars in these animations are very, very small. They're on the order of just probably a few pixels in this image, in these simulations. And all of the stuff that you see coming out is mass that's being lost from the stars due to the stellar winds. And what ends up happening is one of the stars will have a slower, more dense wind, which is kind of on the left-hand panel, it's represented by the more red and yellowish colors. And then one of the other stars will have a faster, lower density wind, but that lower density wind has a lot of momentum because it has a very high velocity. And so it can push and create a cavity in the wind of the other star. Now, what happens, though, is that mass has to be conserved. And what ends up happening is all of the mass that would normally be in this cavity, it gets pushed and compressed into the walls of the shock. And when it does that, the density gets enhanced in the walls. And then we think that different cooling processes can take place, namely things like optically thin radiative cooling. And what that does is you get a runaway effect. So the density goes up, the stuff can cool more efficiently, which allows the density to go up even more, which allows the cooling to become more efficient. And then you get a runaway effect where eventually the stuff cools and gets dense enough to a point where things like complex molecules and dust can form. And so we think that is what is exactly happening in systems like WR140. Okay, so what's new since 22? What have we learned from James Webb since we did these initial observations? So these are going to be the main topics of the talk. So the first is we now have proof of real astrophysical outflows. And we also now have associated proper motions of these dust shells. And I'll talk about and show that. And then also we've started doing analysis of the spectra to get a little bit of a better idea of what's going on in terms of the types of molecules that are forming and what that tells us about the chemistry that is going on in these types of systems. So I'll be talking about these things that are called aromatic infrared bands, and I will summarize exactly what these things are, these AIBs, and then I'll talk about the results of the first analysis of these infrared bands and these spectra. So the first thing we have is a observed motion of the dust shells. So what I'm showing here on this slide is actually a difference image, or it's actually two images in one. So it is an overlay of the original observations that we took in 2022, and then the new observations that were taken in cycle 2, which was a couple of years later. And what you are seeing is the cycle 1 is shown in orange, and then the cycle 2 is shown in blue. And we can see pretty clearly that the blue is sitting farther out from the orange. And I'll show this, actually, I do have an animation that shows a blinking between the two images, which will more clearly show this, this motion. And we did these observations at a couple of different wavelengths, but here I'm just showing the 7.7 micron image. And the other thing to know about this is we were very, very careful to make sure that the images from cycle to cycle were aligned as accurately and precisely as we could possibly get. So these images are aligned to within 0.1 pixels, which corresponds to a maximum distance uncertainty of about 18 astronomical units at the assumed distance of WR140. The other way that we can check for how good the alignment of the images is actually to look at the background stars, or in some cases the foreground stars. And if we look at these background and foreground stars, we see that they line up essentially perfectly, and they're nice and white, right? So our stars in the foreground and background line up really, really well. And so we know that our images are aligned well. So here is kind of a zoom and kind of a separation between the two images. So on the top row on the left is the original July 2022 image. And then there's a panel A that is a zoom of some of these dust shells. And then here we have the cycle 2 observation that was taken in September of 2023, where we have this little box B. And then the far right panel is a comparison of the cycle 1 observation, which is from box A, and then the cycle 2 observation, which is box B. And you can very clearly see the difference in position of the dust shells. And then the bottom image is just a reference to give you an idea of what the spatial scale is, what the filters were for creating the image, and then the directions of north and east for these images, just to give you some context. But again, images are very nicely aligned, and we can see this motion. If you're still not convinced, here are animated videos of the cycle-to-cycle variations from the original JWST observations. Again, at 7.7 microns. And so the top is the entire system. And then the bottom is a zoom of that C1 dust feature that I had mentioned before. And you can kind of see again the motions, the astrophysical motions of the shells. And then this is a slightly different orientation of the images, but the color images being blinked between 2022 and 2023. And again, we can see the spikes, the diffraction spikes, and the instrumental artifacts and how they change, but the actual dust shells are very, very similar, and we're seeing the outward motion as these shells are moving outward into the interstellar medium. Okay, so what I wanted to show here that's going to be important for some of the later discussion is how we did some of the more detailed data analysis and how some of the substructure that we saw in the dust shells is persisting. So in the left image, we have, so this has been oriented to make it a little bit easier to visualize where north is up and east is left. So we have the overall image of the entire system. And then we have a couple of different boxes that are different colors. And each box of each color tracks a different physical feature in some of the shells, because we wanted to use different features to do the proper motion study and to also analyze the spectra to see if we're seeing the same thing at all locations. And then also for consistency's sake. Now, you may be wondering what these red lines are. Well, one of the things we wanted to do is we didn't want to just take a single line through a single feature and then base the analysis off of that. So what we did is we actually did 10 radial profiles or radial cuts through each feature, and then used the mean of those 10 radial slices in order to do the calculations and do the proper motions in order to give us a more robust result. And so on the right, we have the zooms of the different boxes showing some of the substructure in the dust shells and how the substructure persists from cycle to cycle. So the arrows are pointing to substructures that we identified and showing how those substructures in the dust shells move over the course of the roughly year in between the when the images and spectra were taken. Okay, so now what I'm going to do is I'm going to talk a little bit about those radial flux profiles. And so what we did is so the images I've been showing have all been at 7.7 microns, but the nice thing about JWST, obviously, is we can get observations at other wavelengths. And so this is showing those radial flux profiles as a function of distance from the stars. But for the three different physical features, C1, E, and C0, and then also at different wavelengths and for each of the two cycles. So the dashed lines are the observations that were done in cycle 1 in 2022. And then the solid lines are all going to be the observations a little more than a year later. And then the different colors of, say, blue, green, and red, those just correspond to the different wavelengths of the observations. And then, again, each box is showing for a different feature, right? A different feature. And the plots are the averages or the median, I should say, of those 10 radial profiles. So this is kind of showing the difference, right? And so this is good for figuring out how the dust shells are moving. And then we can use these radial flux profiles to get an idea of what the proper motions are. And then the gray vertical lines are just intervals of every 2 2/3 arc seconds, which correspond to about 4,380 AU for the assumed distance to WR140. And we picked this interval because this is the interval that is the median separation between peaks. So basically, it's the median separation between where the dust shells are. Okay, so the results of the analysis. So I'm not going to go into the gory details or how the sausage was made, so to speak, in terms of computing the proper motions. I will just summarize the main results and comment on them. So we were able to get proper motions, and we were able to get both projected proper motions and deprojected proper motions. So the projected proper motions for that C1 feature for the shells comes out to about 332 plus or minus 20 milliarc seconds per year at each of the wave bands. And when you convert this into a actual physical speed, we see that it comes out to roughly about 2,500 or 2,600 kilometers a second. And this is actually pretty nice because that is really, really close to the estimated terminal wind speed of that Wolf-Rayet star, which is about 2,860 kilometers a second. Now, keep in mind, one, these are projected proper motions, so projected on the sky. And then the other thing is getting distances to stars, as I'm sure you're all aware, is a very difficult thing. And getting very accurate distances, parallax is one of the best ways to do it, unless you can get really good orbits and use Kepler's laws. So the 1.64 kiloparsec distance is kind of what's estimated based on the orbit, the observed orbit of the system. But if we were to use the Gaia data to release 3 parallax measurements, which give a slightly different distance, we would get speeds that are higher by about 200 kilometers a second, which would actually bring things into even better agreement. So it's all a matter of what distance you assume to the system. But in any case, whether you're using the orbit or whether you're using the Gaia parallax measurements, we're still really close to the wind speed of the Wolf-Rayet star, which is a really good sign. It means that the shells are outflowing basically at a roughly constant velocity, at least as far as we can tell. Now, it turns out that that other feature, one of the other shells in the other directions, happens to be projected close to our line of sight, which allows us to get a deprojected velocity for the shells in that direction. So we know the inclination of the orbit relatively well. This theta parameter in this equation is basically, if you recall that computer animation that I showed, there was a wedge that was kind of cut out in the wind of one of the stars. And that theta angle is basically related to the angle of that wedge. So it's what we call the half opening angle of the colliding wind interface. And so since we know WR140 very well, and we know its inclination pretty well, and we think we know that opening angle pretty well, we can use these to get a deprojected proper motion and velocity for the shells. And again, what we find are numbers that are consistent with what we might expect based on the terminal speed of the wind from the Wolf-Rayet star. Now, one of the things that's also very interesting about these proper motions is that we found, with the data that we have, no statistically significant dependence of these velocities on the wavelength, which is actually kind of good, right? So we're getting observations at different wavelengths, and we're finding that we're basically finding roughly within the errors the same speed, right? And so that also is kind of a good sign, because we wouldn't really expect that these shells, if the shells are actual physical objects that are moving through space, right? The speed at which they're propagating shouldn't depend on the wavelength of the light that we're looking at them with, really, if all of the emission is coming from the shells. So we find that that is the case with these observations. The other thing that we found is that we did not find any evidence for acceleration or deceleration of the dust shells. So to within the uncertainties, we did not see any acceleration or deceleration. They're moving at pretty steady, consistent velocities that are really close to the wind speed of the Wolf-Rayet star. So the conclusions of this proper motion study are actually kind of nice. We confirmed that the shells are real. They're real things. They're not imaging artifacts. We can see them moving. They are moving at the expected speeds. They are moving at speeds that are related to the terminal speed of the Wolf-Rayet star's wind. And we were also able to confirm that there's this clumpiness to the shells. So when you zoom in on the dust shells, you can actually start to resolve and see structure. So they're not just perfectly smooth shells. There's clumping. So there are regions that are higher density compared to some surrounding regions that are lower density. And we actually think that these clumps arise from physical instabilities that happen in the colliding wind region. So there's actually a lot of interesting physics that is happening in the colliding wind region as this stuff is colliding with itself, as the two winds are colliding and as the stuff is cooling off. And you get things like Rayleigh-Taylor instabilities and other types of physical instabilities that help the stuff to kind of coalesce and cool off. And we actually think now that this clumpiness is important for the dust formation, because it allows the density to get enhanced. And then the outer portions of these clumps, we think, act as a type of shield from the intense radiation fields of the stars. So the outer portions of the clumps, we think, help to protect the inner regions, so that these complex molecules and dust can actually form. Okay, so now we are going to do a transition to talk about these aromatic infrared bands and how that relates to the study. So the first thing I want to do is just really briefly summarize what are aromatic infrared bands, because a lot of people may not be familiar with these things. So it turns out that these AIBs are an emission feature from polycyclic aromatic hydrocarbons. So polycyclic aromatic hydrocarbons are a type of hydrocarbon that are known to exist in the interstellar medium. They are responsible for approximately 10% of all of the carbon that is in the diffuse interstellar medium. And they are observed in the near and mid-infrared at several different bands. So these are the major bands that, the major wavelengths that these emission features are seen at, but there are a bunch of other minor ones, but these are kind of the key ones. Now, what do they mean? Well, it turns out that when you take spectra of these things, you can divide these spectra into different classes. We just call them A, B, C, and D. And all you really need to know or understand is that each spectral class can be associated with a different type of astrophysical object. So for instance, class A spectra are the type of spectra we see in the interstellar medium of our Milky Way and in galaxies, and also in things like asymptotic giant branch stars. Class B spectra we see in planetary nebula and in young stellar objects. Class C are things like Herbig AEBE stars and T Tauri stars. And then class D are in things like carbon-rich post-asymptotic giant branch stars. So again, the main thing is that these different spectra basically probe different classes of objects, but all of these objects have these polycyclic aromatic hydrocarbons, and they also have high concentrations of carbon to an extent. And so these different classes are just considered to reflect the different types of complex carbonaceous compounds that exist in space and in different astrophysical environments, right? And so it's kind of good to have these things and to look for these signatures in these colliding wind binaries like WR140, because we can then say, okay, well, what type of class does WR140 fall into? And then based on that class, we can say something more about the chemistry that is happening in the environment. So what we did is we went ahead and took a data cube. And here I'm just showing on the left the cube image at 7.1 microns. And this is the, what we're going to do now is we're going to look at the original cycle 1 data, because that is what has been analyzed to date. And the yellow circle and kind of what's the darker region in this image, that is the location of the star, or I should actually say stars. And then the cyan circles, all of these different cyan circles, are different areas, different places where we took spectra. And some of these apertures fall on top of some of those dust rings, and then some of them fall off, are located on areas where there are no dust rings, right? So we wanted to see what was going on both on the dust rings and away from the dust rings to kind of get a better idea, again, of the astrophysical chemistry. So here is just an example, just to give you an idea of what some of these spectra look like. So the column on the left are spectra that were taken located on top of some of the different shells. And then the distances here that you see, those are the distances from the binary star system, right? So as we move out, as we move down the column, we are moving farther and farther away from the stars. And then the letter designation, these are just identifiers for the specific feature. And then here we have off-shell positions. So the very first one at the top is the spectrum on the very center where the stars are. And then moving down, basically these are distances in between the shells where we shouldn't be having basically the same type of spectrum or the same type of chemistry going on. Now, what we did is we did an analysis of these different features, and we also did it at different wavelengths. So we are looking at a couple of different features at different wavelengths here. And the first column is at 6 microns. The middle is a feature that we found at 7.7 microns. And then the last column is a feature at 11.2 microns. And the reason that we picked these particular wavelengths is these are the wavelengths that are known for these AIBs. And so we wanted to take a look at them. And then what we did is we were looking at the peak wavelength, the full width at half max, and the integrated intensity as a function of distance from the star. Now, these might just look like plots of just kind of like random data points. And I want to take just a moment to kind of clarify exactly what we're seeing in these plots. So the whole point of doing this type of analysis is to try to see if a particular feature is showing up at larger distances from the star, or if it's only happening, say, for instance, is a feature only happening on a shell, or is it showing up on both a shell and in that that off-shell region in between shells? And then is it, how is it behaving as we move away from the stars? And the main thing to show here is that what we're finding is that the feature is happening both on the shells and, so a little bit surprisingly, in between the shells. And it is happening with increasing projected distance from the stars. So the best way to understand these plots is that we are seeing features both on and off shell, and we are seeing that these spectral features persist as you move outward away from the binary system. So that's the main thing that you should get from this analysis, but I just wanted to show the plots for completeness. Now, this is where it gets really interesting. The next thing that we can do is we can look at a particular feature and we can compare the spectra to known spectral classes for the AIBs. And so that's what these plots are showing. So in each panel, we are looking at the spectrum from WR140, both on and off shell. So the left column is the spectrum taken on a dust shell, and then the right column is a spectrum or spectra taken at off shell positions. And the left column, we're looking at two different features. So the black spectrum is the feature that we called S1, and then the blue spectrum is just a different dust shell that we called S2. Now, what we want to do is we want to look and see how do the blue and black spectra compare to the red spectrum. So what is the red spectrum? So the red spectrum in each panel corresponds to a different known class of AIB. And so what we're trying to do is we're trying to say, okay, here is what we're seeing in WR140. And then we're going to compare that to what we know and have seen in other astrophysical environments. And we want to know how well do they match up. And that will tell us whether what's happening in WR140 is similar to what's happening in another type of astrophysical system. Now, the only other thing I will point out is that there is contamination from a forbidden sulfur 4 line at about 10.5 microns. It's a known emission line and it doesn't come from dust. So just ignore this feature. So what do we see here? Well, what we find is actually very interesting. When you look at when you look at WR140 and you try to compare it to a class A AIB spectrum, we find that it matches somewhat well, but then deviates a little bit. And the same thing when we look at the off-shell positions. But for the most part, what you'll notice is that none of the blue or black spectra, or very few of the blue and black spectra, match up really well with any of the red spectra. So what that is telling us is that, surprisingly, what's happening in WR140 doesn't match to any of the known other astrophysical objects that we observe. So WR140, what's kind of happening in WR140 with this dust formation and these AIBs is almost a class in and of itself. It's almost a new class of astrophysical chemistry. Now, I say almost because one of the things that you can do is, and one of the things that we did was we looked at our own galactic ISM, and we looked at the spectrum of that and compared that to the dust that's forming in the shells of WR140. And what we found was that the dust that is forming in WR140 in those shells and moving outward is actually very, very similar to the dust that lies in our galactic plane. And so this is actually a really great result because it shows that what is happening in this massive star system and is flowing out into space is what we basically see in the ISM of our galaxy. And so what we think we're actually seeing is the very first initial seeding of the ISM with complex molecules and dust. And the reason I say the very first beginnings is because if you look very closely at where the peaks of the emission are in the spectrum that's taken in the galactic plane, which is the bottom plot. So the peaks have been marked here with these by these red dashed lines. We see that the peaks in the WR140 spectrum are slightly shifted, which means they don't quite match up, right? So it's very close to the spectrum of the galactic plane, but not quite. It's slightly shifted. The other issue, you'll notice that over here at about 11.2 microns, we have a little bit of trouble because there is an AIB feature that is at 11.2 microns. But part of the problem with W140 is it's very hot, massive stars. And so there are lots of helium emission lines that arise and also helium absorption lines. And some of these helium lines unfortunately overlap with this 11.2 micron feature. And so it's a little bit contaminated by the lines that are in the stars, in the stellar system. And so we can't quite say for sure that it matches here on this end of the spectrum due to the contamination by these lines. But in any case, for the most part, it's still, when you look at the other two peaks, it matches, or the other three peaks, I should say, it matches very, very closely. And so this could, I think I'm going to skip over this plot. But basically what it's doing is it's giving us a hint of what's going on. So one of the other things we can do is we can look at the relationship between peak wavelength and full width half max for the different features. And then we can compare the data for WR140 with other known types of objects. So that's kind of what I've done here in this plot. So we have the red data points. So the red data points are WR140 in both plots on the left and right. And then I've put data for the regions where other types of objects exist. So the green box is things like planetary nebulae. The kind of like pinkish box is where we have things like hydrogen poor R coronae borealis stars. And then here we have the regular RCBs. And then the little blue box is just like hydrogen poor planetary nebula. And one of the things that we're finding that's interesting is that instead of matching up to these known AIB classes, we're finding that what's happening in WR140 is actually more similar to the spectra that are seen in these RCB stars, right? So these RCB stars, if you're not familiar with them, they're basically like yellow supergiants, and they also tend to be very, very hydrogen poor. They're mostly helium and carbon, and so we're finding that the spectra are kind of very similar to these RCB stars. So what were the conclusions of this AIB study? Well, one of the things that we found is that the AIBs that are known to exist at 6 and 7.7 microns, which this is due to a stretching mode in carbon-carbon bonds. It's been detected both in the dust shells, but also at features much farther than shell 1. And these features are particularly prominent in the on-shell positions compared to the off-shell positions. We do see hints of this 11.2 micron AIB, which is due to a kind of bending mode between carbon and hydrogen in these polycyclic aromatic hydrocarbons. So basically, you have a carbon atom and a hydrogen atom, and it's kind of bending, and it gives rise to an emission feature. And we've seen this tentatively around shell 2, but again, the problem is that it's possibly contaminated with those helium lines, and we could not identify this feature on shell 1, at least not to any confidence. We also found that the spectra do not really coincide with any of the known classes, which implies that the structures of the carbonaceous compounds that are forming in WR140 and likely all of the other similar massive binaries like it are a bit different from other known astronomical objects. We found that, this is just an extra bullet point, we found that the integrated intensities, when we normalize by the 11.2 micron emission, we get strong positive correlation, which is expected because that's what's seen in basically all other astrophysical objects. And then we found that the peak wavelengths and full width at half maxes of the different features of at least the 6 and 7.7 micron features, because those are the ones that we could clearly identify, they actually agree to a large extent with similar features that are seen around these hydrogen poor R coronae borealis stars. And what this does is this is suggesting that what's happening is that the dust is actually starting to form near the Wolf-Rayet star, which has a lot of carbon, and somehow the dust that is forming with the carbon from that Wolf-Rayet star is not being contaminated by the hydrogen-rich wind from the O star. So that's why this connection to these R coronae borealis stars is important. It's because these R coronae borealis stars are very hydrogen poor. They have carbon, and we see these AIB spectral features in the PAHs. And the fact that we're seeing something very similar in WR140 means that we also have a very hydrogen poor environment where the dust formation is occurring, which means that somehow, and this is kind of another question that we're going to have to answer, somehow all of the hydrogen that's in the other star's wind, the O star's wind, it's not contaminating the process somehow. So it's actually not contaminating and contributing to the dust formation. And so that's going to be another thing that we're going to have to figure out and solve in the future. So what does this all lead to? Well, we now have a little bit of a possible chemistry scenario. So we think what happens is that the hydrogen poor carbonation compounds form initially within a short time scale after the two winds initially collide. So because we're seeing these features in the very first ring, and we know what the orbital period of the binary is, we can estimate the initial time scale for formation, and we're finding that it's less than or about 5 years after the wind-wind collision. And we think that this is the origin for the two AIB spectral features that we see at 6 and 7.7 microns. Hydrogen is then provided by the O star's wind, but only a little bit. It's not like a significant contamination. It's just enough so that we can start forming these polycyclic aromatic hydrocarbons. And then the hydrogen-attached carbonaceous compounds form and then survive farther out in shell 2, and then possibly even farther from the second shell. And then it would be from these farther shells that we would get the 11.2 micron spectral feature. And then eventually, we think that after hundreds or thousands of years, those dust shells flow out into the interstellar medium, where they get processed further by things like stellar radiation fields, cosmic rays, all of those different types of things, further process the dust, and then we eventually end up with stuff that looks like the average galactic plane interstellar medium. And so now we at least have a little bit of a possible chemistry scenario for what's happening and how the interstellar medium might get seeded by carbonaceous compounds and dust from these systems. Okay, so I'll just conclude with this brief summary slide to just kind of sum up everything that we talked about. So what have we found today? What have we learned today? So the first is that these shells are real, which we had always kind of suspected, but it's always good to prove it. And they are expanding at relatively constant velocities that are consistent with the known terminal speed of the Wolf-Rayet star's wind. And we see very little evidence of any type of acceleration or deceleration, which is important because it kind of tells us about what other forces may be at play in the system. With the detailed observations, thanks to JWST, we can see substructure in the shells, and we can see that this substructure survives for at least a year or probably even more. And we think that these clumps are important for dust formation and also shielding. We see these 6 and 7.7 micron AIB spectral features detected further than shell 1. And we find that they are also more prominent on shell than off shell, which kind of makes sense, right? You expect the spectral feature to be stronger where the dust and molecules are forming. The other 11.2 micron AIB is tentatively detected around the second shell, but it could be contaminated by the helium lines, and we couldn't find it on shell 1. The spectra are not typical of the normal major classes that astrophysicists are familiar with, which tends to suggest that these compounds, these carbon compounds, are different from those in that we usually find them in. And instead, we find that the spectral features actually agree better with these R Coronae Borealis stars, which tells us more about the chemistry and suggests that the dust forms pretty early and close to the carbon-rich Wolf-Rayet star, and it's not significantly contaminated by the hydrogen-rich O star wind. And with that, I thank you, and I'm happy to take any questions you may have.
Thank you so much for the presentation. That was, I mean, you took something very complex and broke it down. I guess for my basic understanding, my question was when you were talking about the shells and the spectra. I mean, there are differences, but had you indicated that there was a lot of similarity between the on and off shell portion spectra as well, and what the explanation for that would be?
So probably what's happening is, so one of the things I didn't really talk about in a lot of detail was let me see if I can find the slide, was like the integrated intensity ratios. So the best way to think about it is like this. So the dust shells form in these compressed rings, but the two stars that are at the center of the system, they still have a stellar wind. They still have stellar winds that are continuously blowing outward. And so probably what's happening is dust is forming in the compressed shell, but then the stellar winds are kind of like any other wind, and it's blowing the dust and it's kind of blowing it out a little bit into the empty spaces in between the rings. And so there's some residual that is sitting in between the rings that gets blown out by the stellar winds, and that becomes detectable. So I have a feeling that that's probably what's actually happening. The dust shells are kind of being ablated by both. I should actually say both the stellar winds and then also the radiation fields from the stars, because those stars are so bright that there's probably a radiation pressure also pushing on the dust shells and helping to ablate them slightly.
All right. And then a question from Steve Jacobs, he wrote in the chat, why are the rings not decelerating?
That's a really good question. It's probably just coincidence in the sense that it's probably WR140 probably just happens to be in a region where there isn't a lot of other surrounding interstellar medium. And I have a feeling that if we were to look far enough, you might actually expect the stuff that is coming from WR140 to eventually hit something and slow down. I think the problem is that we've kind of reached the detection limits with JWST, and so we just don't see that. We're just not able to see that farther out. But it's an excellent question, and I think it's actually telling us something about the surrounding environment of WR140, which is that there just mustn't be a lot of stuff there to slow it down. So there's just nothing there to slow it down, and so we don't see it. Also, interestingly, you could also ask kind of a similar question, which is why are they not accelerating? Because like I just said with the last question, there is radiation pressure and the winds of the stars still pushing on these shells. But apparently, at least according to the observations, it's not enough to significantly accelerate the shells or drive them out any faster. So probably the stuff has just reached the maximum speed that it can reach, and that's it. But it's a good question.
Okay, and then a question from Nathaniel Bates. Which hydrogen-rich carbonaceous materials form in the last stage?
That's a really good question. So honestly, I'll be honest with you. I'm not an ISM or an astrophysical chemistry expert, so I don't really know I guess the best thing to do, if I can go back real quick, it's probably going to be things that are more complicated PAHs. And then there can probably be, so I'm just trying to get back. Yeah, here we go. So we can get these HACs, these QCCs. So basically things like you can get like maybe buckyballs, Buckminster fullerenes. You might be able to potentially get some other hydrogen bonding to go on, but to be honest, I don't know exactly what some of the other chemistry might be as once you go farther out. It also gets a little bit more complicated because then you have to start taking into account how everything is being bathed by everything else in the galaxy. And to be honest, I don't think astrophysicists have really solved that puzzle yet. Astrochemistry is still kind of a very growing field, I should say.
Okay, a question from John Corlett. Is the dust chemistry evolving further as it moves away from the stars beyond the stated shell 1 and shell 2 evolution? And why don't we see symmetry in the image of rings around the stars? Like that half is missing. And I had wondered the same thing too.
Yes, so I can actually, I'll see if I can find it. So yes, so the first question is yes, the chemistry is changing as it evolves. I mean, as the stuff moves away from the stars, and that's to be expected because it's cooling. The temperature is changing. You're getting farther from the radiation fields. You're getting exposed to other things coming from the galaxy. You're getting exposed to other stuff in the surrounding ISM. And so, yes, the chemistry is definitely going to change. But exactly how it changes and on what time scales and in which ways, we're not completely sure of. Um, am I still sharing my screen? Can everyone see this slide that says geometric dust model?
Yes.
Okay, so so that's also a really good question. Why are the shells not symmetric? So it turns out that the reason the shells are not symmetric is it happens to just be the orientation of the binary projected on the sky relative to Earth. So there's no special orientation for a binary in space, right? It can be, and Earth, despite what we may think, is not necessarily special in terms of its location. And so this WR140 could have any random orientation on the sky that it wants to have. And it just so happens that when you orient the binary at the angles that we know that it's oriented at, when you take all of those dust rings and you integrate the emission from them along the line of sight, what you end up getting is the rings where we see them. So this is an illustration. This slide is kind of an illustration of that model. So on the left, it shows kind of the central binary. So the cyan dot would be the central binary. And then if you want to see the orientation of the central binary on the sky, that's the inset with the Wolf-Rayet star and the O star marked, and then the direction of the orbit. And here what's shown is just the first dust shell. So say after one orbital period, what would be the distribution of dust in the shell? And how would that dust be projected on the sky? And what would we see from Earth? And so that is this. And then if you wanted to see, if you wanted to have a little bit better idea of what the dust shell looks like, the right panel is, imagine I could get in a spaceship and travel to WR140 and then hover above the binary and look down on it. What would I see? That is the view that you see. And then the arrow where it says to observe it, that's actually towards Earth, right? So it's all a matter of the orientation of the dust shells projected on the sky relative to us. And then when you just evolve this model, when you evolve this simple geometrical model for many, many orbital periods, and then create the projected image, that's this. That's the image on the right. And it matches up, surprisingly, it matches up really, really well with what we actually see. So that's a good sign. That means we've pretty much got it right. But yeah, it's just the orientation of the system on the sky relative to us. That's just how it is.
All right, are there any additional questions? You can unmute if you want to talk or put them in the chat. That might be it. Okay, well, thank you, Professor Madura.
Sure.
And we will see you again next year in February. And I just wanted to make a quick correction. Yeah, everybody's clapping.
Thank you so much.
stated that the next astronomy night, public astronomy, is April of next year. So actually, end of March. So our next program will be March 21st. We'll see you guys up on the mountain. Okay. Enjoy your night, everybody. Thank you.
Thank you.
All right.
Thank you so much, everyone, for the opportunity. It's great sharing this work, and I'm very happy to have joined you tonight.
Thank you so much again for your time. I know it's very valuable.
Yeah, no worries. Thank you for coming.
All right. Have a good night, everybody.
Good night.
Good night. Good night.